Here's a quick run through of problem 13. We have a current source with an RLC circuit in parallel. We have IM, which is the maximum or peak current, cosine 2 pi f plus the phase angle. If IM is 1 millivolt and the phase is 0 degrees and the frequency is that, we get omega to 2 radians. All right, and we can just plug that into the equation right there. But the shorthand would be IM with a phase angle of 0. Now it's true that we put this in degrees and this is in radians. Won't work in a calculator, but we write this out all the time. So let's find the impedance. The resistance is 2, so the impedance is 2. Impedance of the capacitor, we can find that is minus 0.25J. Impedance of the inductor. So method 1 is we find the equivalent impedance of everything. Then we take that source current, multiply it by the impedance, get the voltage. Then we find the current through that branch, which is simply the voltage divided by the impedance of the capacitor. Method 2 is current division, where we find the parallel combination of the resistance and the inductance impedance, and we just write this out directly. The source times the parallel combination of the other impedances divided by the sum of the current we're looking for with the parallelized impedance. Both should be in polar coordinates at the end, and then you would just write down in the MyOpenMath, I see, whatever value you got for that, times cosine, 2 times pi, actually, times that number, times t, plus whatever phase angle you found. Now if we want to do it numerically, we have Z equivalent, 1 over each impedance, which gives us 0.5 plus 0.4J, remembering that 1 over minus J gives us plus J. And now the inductance admittance is minus 0.25J. Then we need to invert that, which is best to do with polar coordinates. 1 is a magnitude of 1 with a phase angle of 0. Here's our real and here's our imaginary. The magnitude, 3.78, and a phase angle of 82.4. So once we invert that, we have our equivalent impedance. To find the voltage, we just take our 1 milliamp phase angle and multiply it by our impedance. And yeah, this magnitude times this magnitude equals that magnitude. And since we're multiplying vectors, we just add the angles. 0 plus minus 0.82. If you're unfamiliar with that, it's well detailed in the book under these polar rules. Now to find the current, it's just the voltage divided by the impedance. This is purely an imaginary impedance, so the magnitude is plus 0.25, not minus 0.25, and the phase angle of minus J makes it minus 90. So we just divide these two numbers, we get that. We subtract this from that and get a positive phase angle, and then you could be able to write in your MyOpenMath this number directly, times cosine, 2 times pi for pi, times whatever frequency from the problem, times t, plus that phase angle. And I verified this in LT-Spice, and at first, yeah, it was shocking, because this current magnitude is greater than the current of the supply. How is this possible? Well, Kirchhoff's current law is that the currents into the node are the currents out of the node. So we have our phase currents, and this is all from LT-Spice. And if you look at if I tried to draw these to scale, you should see that the vectors should add back to the 1 milliamp with 0 phase. So I convert all these to Cartesian, and when I sum it up, I get close to the 1 millivolt that I started with. When I sum these up, I get very close to 0J. Why isn't it exactly 1 milliamp and exactly 0J? It's just numerical rounding errors. I hope this helps.